Often in science we want to make discoveries, but we want to be certain or at least confident that our discoveries are real rather than just a fluke. In order to prove with statistical certainty that a result is significant, scientists tend to use an unusual tactic. They try to prove that there is actually no effect of the independent variable on the dependent variable. This is called the null hypothesis. As an example, let's suppose that we wanted to show that studying for your physics exam improves your exam score. We could randomly divide a large class in half. Group A, who are allowed to study for the physics exam, and Group B, who are not allowed to study for the physics exam. The breaking of the population into two random groups is sometimes called A-B testing. We then collect the results from the exam, and we do some calculations and discover that the average from Group A is 70%, with a standard error of 6%. We discover that for Group B, the average is 40%, with a standard error of 8%. Now, rather than assuming that studying made a difference, instead we'll assume that studying made no difference to the final score. In this case, the fact that Group A scored 30% higher than Group B is just a random fluke. We then ask, what is the probability that such a great difference in grade could occur just by random chance? One way of doing this is by looking to see how many standard errors there are between the two values. If we do a subtraction, using our new uncertainty formulas, we get 70 plus or minus 6% subtracting 40 plus or minus 8% gives us 30 plus or minus 10%. Our null hypothesis would be that 30 plus or minus 10% here is actually 0 within error. So the question is, what is the probability that this would happen? Well, to figure this out, let's consult our probability distribution. So if we have a look, our 30% is 3 standard deviations above the expected mean of 0. So, looking at our graph here, the probability of this occurring is less than 0.1%. So therefore, we can be pretty confident saying that this is not a fluke. In fact, we could say this is not a fluke with 99.9% confidence. Therefore, the null hypothesis is wrong. And studying must influence the student's results on the physics exam. In physics, rather than talking about percentage confidence, we tend to talk about the number of standard deviations, or errors, the number of sigma, between our data and the null hypothesis. In general, different fields use different levels of sigma to prove their findings. So, just to explain this table, we've got a number of different scientific fields down the left-hand side here. So, biology, psychology, clinical trials is one. Then we've got general physics, we've got particle physics and astrophysics. And then the data we're looking at here is the number of sigma that you definitely need, or that you usually need in most journals to be able to publish your findings as a success. And then the chance of fluke that corresponds to that number of sigma. So in biology and psychology and clinical trials, generally it's expected that you will get at least 5% significance to within 5%, or at least 2 standard deviations away from the null hypothesis. However, this does mean that 5% of all the studies in theory will actually be false positive results, that something occurred just by random chance rather than it actually being a new discovery. Now, most physics studies require, and most physics journals require 3 sigma. So that means that the chance of a fluke is less than 0.2%. In particle physics, they are particularly rigorous. In order to have a particle physics discovery, you need at least 5 sigma, or you need to have 5 standard deviations away from the null hypothesis. This means that the rate of flukes is 0.00003%, so it's extremely unlikely. In astrophysics, they're even stricter when they're making their discoveries. Generally, you need 6 standard deviations away from the null hypothesis to be able to prove a discovery, or for a discovery to be accepted. Therefore, the chance of fluke is insignificant. Now, for a number of fields, including physics, chemistry, biology, and psychology, there's actually a bit of a crisis of reproducibility, where it appears that a significant portion of the published science, in fact more than 20%, is actually false due to these flukes. For the most part, this doesn't happen in particle physics and astrophysics because of the stronger statistical requirements for publication to be accepted.